Hey guys, welcome back. Let's begin with our part 1. So the topic of part 1 is sequences, limits, and completeness of R. So in this part I will talk about what is a sequence and what is the limit of a sequence and what we mean by saying that R is complete. Let's start with sequences. I want to recall a notation. So this funny symbol R is the set of real numbers. So it is a set of real numbers. And real numbers, you can imagine it is the collection. A real number is a point that is on the real line. So you can see this is a real line. And on the right end is positive infinity. On the left end is negative infinity. And we collect all points that is between negative infinity and positive infinity. And this funny notation R is the set, the collection of all the points in R. Alright, so let's look at our first definition. This definition is talking about what is a sequence. So a sequence, a sequence in R is an infinite order list of numbers in R. Infinite order list of numbers in R. So this is a definition of a sequence. And normally we denote the sequence by an parenthesis n from 1 to infinity, or simply parenthesis an. And because this is the first definition in this course, so normally in a definition when you see something that is in boldface, like the sequence in here, then this is the terminology or the mathematical object that it is defined in this definition. So this definition, sequence, is the new terminology that is introduced. And what the meaning of this new terminology is, it is an infinite order list of numbers in R. And also notations will also be in boldface. Alright, so let's look at 2 examples of a sequence. So the first example is if we consider this list, order list of numbers, -1, 1, -1, 1, -1, 1, -1, 1, and so on, and just goes on. And then this is a sequence in R because it is an infinite order list of numbers. So notice that actually in sequences we allow repeated value to show up. In this sequence, allow the repeated value. Basically, there are only 2 values, -1 or 1. And for odd terms, we got -1, and for even terms, we got 1s. And this is a sequence. And sometimes when the sequence has some kind of special rule according to n, then we can write it compactly. So for this sequence, actually, we can write it as -1 to the n from 1 to infinity, because -1 to the n, when you take n as an integer 1, 2, 3, 4, then it just follows the same rule as the sequence we wrote here. Alright, so this is an example of sequence. A second example is here. So 1/2, 1/4, 1/8, 1/16, and so on. This is a sequence in R. Of course, it's a order list of real numbers. And also it follows some rule. The rule is 1/2 to the n. So we can actually write it compactly as 1/2 to the n for the sequence. Alright, so this is examples. These are examples of sequences. You can build your example. You just have to write a lot of numbers, and then if you give it some rules, that will be better, so that you can write it in a compact form. Okay, so next I want to talk about what we mean by the convergence of a sequence. So since we want to talk about a convergence of sequence, we first have to give a sequence. So let n from 1 to infinity be a sequence in R. And also, because we want to talk about the convergence, we want to talk about where the sequence converges to. So we have to also have a number. So a in R is a real number. And we say that this sequence an converges to a. So this is the term that we want to define, the concept of convergence. We say that a sequence an converges to a as n goes to infinity if the following is true. So this is a logical statement. So let me explain. There are some terminologies that I mean, there are some symbols that you may not see before. Let me explain. So here's a symbol, here's another symbol, here's a abbreviation. So this upside down A is actually a symbol that is usually used in logic. It is called for O, or some people will say it's for any, but yeah, I'll just stick with for O. And this funny it's not upside down, it's actually left and right opposite E. So this E is actually meaning that there exists. Alright, and here's the abbreviation, SNT. And in this course, SNT, S dot T dot will mean such that. So yeah, these are the two symbols and one abbreviation that I want to introduce. It is normally used in a lot of courses, especially math courses. So yeah, it's better to tell you this here. Alright. Okay, so let's look at this logical statement. This logical statement is basically for all epsilon greater than 0, there exists an epsilon in... Oh, by the way, here's another symbol. So this is a funny n. Maybe I'll erase it. So this funny n is the same, kind of similar to the funny r here. The funny r denotes the set of real numbers, and this funny n denotes the set of natural numbers. By natural numbers in here, we will mean positive integers. So it's actually the set of positive integers. 1, 2, 3, 4, 5, and so on. So this funny n is this set. Alright, so this logical statement is saying that for epsilon greater than 0, there will exist an epsilon. And epsilon means that it's something that depends on epsilon. And this number is in the natural numbers, such that the absolute value of an minus a will be less than or equal to epsilon for all n greater than or equal to an epsilon. Okay, so this may looks a little bit more mysterious at first glance. So let me talk about the idea of convergence. So here is the idea of convergence. The idea is this. We want that as n goes up to infinity, the sequence an, the term an will be arbitrarily close to the number a. This is what we mean by convergence, right? Intuitively, when n goes up, when n is very large, then the an should be very close to a. And if n goes up to infinity, then an can be arbitrarily close to a. So how do we write this down concretely? Let us to interpret this idea in other words. So in other words, no matter how small an error is given, so given an arbitrary error, there should be a sufficient index. Sufficient index is the n epsilon. So if n is sufficiently large means that there is a sufficient index such that if n is greater than this sufficient index, then it's called sufficiently large. So if we are given an arbitrary error, epsilon greater than 0, then there is a sufficient index, an epsilon, such that when n is greater than or equal to an epsilon, which means it is sufficiently large, then the difference between an and a will be smaller than the error. So the difference between an and a is measured by the absolute value of an minus a. This is the distance between an and a. So yeah, let's look at this sentence again. No matter how small we are given an error epsilon greater than 0, we can find a sufficient index, an epsilon, such that when n is greater than an epsilon, the difference between an and a should be less than that error. So this is a concrete interpretation of how we should look at the limit, or we should talk about the concept of convergence. So go back to the logical statement here. So logic statement is basically what we wrote in the second dot bullet points here. So for any epsilon greater than 0, which represents the error. For any error greater than 0, then we can find a sufficient index such that if the index n is greater than the sufficient index, we actually has an and a in between. The distance between an and a is less than or equal to the pre-assigned error. So this is what we mean by convergence. So we say that an it converges to a as n goes to infinity if this logical statement is true. Notice that here's a for epsilon greater than 0, so we have to check for every epsilon whether this kind of an epsilon exists. If this is the case, then we say that n goes to a as n goes to infinity. Alright. So yeah, because these words an converges to a as n goes to infinity is too long, so sometimes because mathematicians like symbols are easier to write down. So most of the time we'll write limit n goes to infinity an is equal to a, which is equivalent to an converges to a as n goes to infinity. Okay. And here's another terminology, it's called convergent. This is an adjective because converge is a verb. So this is a verb. And this is an adjective. Alright, so sometimes we want to use adjective. And we say that a sequence is convergent if it converges to somewhere. That means if there is a real number a such that an goes to a as n goes to infinity. Otherwise, we say that the sequence is divergent. So divergent is basically the opposite of convergent. Actually, the negative of convergent, negation of convergent. And sometimes we use the phrase the limit of an exists by saying that an converges to somewhere. There exists a such that an converges to a. Yeah. And also we call the number a the limit of the sequence. So when an goes to a as n goes to infinity, we say that a is the limit of the sequence. So notice that in this definition we define the concept of convergence. An converges to a as n goes to infinity if the following logical statement is correct, is true. And also introduce a notation, limit n goes to infinity an is equal to a. This is a notation. And also define the adjective convergent and divergent. Then also the phrase the limit of an exists. And also we define the limit of a sequence. Yeah, the limit of a convergent sequence. Yeah, if an is convergent, then the place where the sequence converges to is called the limit of the limit of the sequence. All right. Yeah, there's another point I want to mention because the notation n epsilon is sometimes a little bit redundant. It's kind of necessary to indicate that epsilon plays a role in an epsilon, because for different epsilon, then you may have different n epsilon. But sometimes people will think at the epsilon, the subscript epsilon is kind of redundant, so we just simply write n. So next time or somewhere else, if you see n, then you have to keep in mind that this n actually depends on epsilon. Okay, so let's now look at one example. We want to show that the sequence 1 over n goes to 0 as n goes to infinity, or equivalently, as we write in notation here, limit n goes to infinity 1 over n is equal to 0. Okay, so just a reminder, this is the same as saying that this sequence 1 over n from 1 to infinity. This sequence goes to 0 as n goes to infinity. Alright, so actually we have to follow the logic statement here. And because this is on the previous slide, I will rewrite it here. So limit n goes to infinity 1 over n equal to 0 is actually equivalent to for all epsilon greater than 0, there exists an n depending on epsilon, which is a natural number such that 1 over n minus 0 is less than or equal to epsilon for all n greater than or equal to n. Just a reminder that this n actually depends on epsilon. All right. Okay, so this is what we want to prove. So we want to prove this statement here. So you can see here. Okay. So yeah, this statement, to prove this statement, basically we have to check for an arbitrary given epsilon whether we can find the corresponding n depending on epsilon such that this statement is correct. 1 over n minus 0 less than or equal to epsilon for n greater than capital N. So to do this in mathematics, we actually, the first step is to let an epsilon greater than 0. So if we let this epsilon greater than 0, because we don't specify what epsilon is, we don't specify epsilon is equal to 1 or equal to 2 or equal to 1/2 or and so on. So the following statement will work for an arbitrary epsilon. So if we let an arbitrary epsilon greater than 0 and also find the corresponding n epsilon without really using any kind of specific number for epsilon, then actually this argument will work. So if we let an epsilon greater than 0 and also find an n epsilon such that 1 over n minus 0 is less than or equal to epsilon for n greater than for all n greater than or equal to n epsilon, then actually we're done. So the first step is to let an epsilon greater than 0 and try to achieve this. If we achieve this, then we are basically done. Because epsilon is arbitrary, then we really prove that for epsilon greater than 0, there exists n in n such that 1 over n minus 0 less than or equal to epsilon for n greater than capital N. Alright. And actually you can notice that 1 over n minus 0 with absolute value is the same as 1 over n because 1 over n is positive and 0 is 0. 1 over n minus 0 is 1 over n. The absolute value is 1 over n. So we can simplify this term as 1 over n epsilon less than or equal to epsilon. So actually this is our goal. We have to find an epsilon such that this is satisfied. Alright, so here it is very simple to prove. The key idea is that we can let an epsilon equal to 1 over epsilon with a ceiling function. Okay, so there are two things I want to explain. The first thing is this notation. So here is 2 dots and the equal sign. In mathematics, this means define us. Yeah, because there are 2 dots. That dots started with a D, so it's defined as. Define equal to this. So basically we define the n epsilon as the ceiling function of 1 over epsilon. And what is the ceiling function? The ceiling function is the smallest integer. So okay, the ceiling function, the definition is here. If we put a number inside the ceiling function x, okay, so the ceiling function x, ceiling function of x is the smallest integer n x such that n x is greater than or equal to x. So for example, like if we take the ceiling function of 1/2, then this will be equal to 1 because 1 is the smallest integer that is greater than or equal to 1/2. And also like if we take like 5 over 2 ceiling function, then because 5 over 2 is 2.5 and 3 will be the smallest integer that is greater than or equal to 5 over 2. And this is the same for negative numbers. So like if this is negative 5.6, then this will be equal to negative 5 because negative 5 is greater than negative 5.6 and is also smallest integer that has satisfied this condition. Alright, so this is ceiling function. The reason why we take ceiling function is because we then have this property. Because we know that ceiling function of x is always greater than or equal to x. Yeah, ceiling function only has this. Let me rewrite it. Hold on. So the ceiling function of x is always greater than or equal to x. This is always true by definition. So because we set an epsilon equal to 1 over epsilon ceiling function, we must have an epsilon greater than or equal to 1 over epsilon, which is this inequality. Or we can take the reciprocal on both sides so that we get 1 over an epsilon less than or equal to epsilon here. So what is the benefit of this? If we have this inequality, then actually if n is greater than or equal to n epsilon, then we of course have 1 over n less than or equal to 1 epsilon, because we take the reciprocal for this one. And because 1 over n epsilon is less than or equal to epsilon, so we also have the second inequality. This makes that 1 over n is less than or equal to epsilon for any n that is greater than or equal to an epsilon, which is what we want. Recall that this is what we want, right? So this is wanted. And by taking an epsilon greater than or equal to 1 over epsilon, we actually achieve the wanted statement. And this completes the proof. Yeah. So proof complete. So the key idea is just simply take an epsilon equal to 1 over epsilon ceiling function. Then the following arguments will automatically follow.